Hi, my name's Max Kreil. I'm an associate professor at the Monash Biomedicine Discovery Institute. I'm going to show you today about how we can make peptides with complex proteins known as non-ribosomal peptide synthesis. And I wanted to do that with my children's toys because it's a complex process, but it's an important one if you want to understand how we can make new antibiotics to fight against superbugs. So this represents a peptide antibiotic. In the case of the systems we work on, it's actually vancomycin, a last resort against serious clinical infection. Now you'll notice that it actually is comprised of beads, and so you'll see that there are 7 different beads. What these actually represent is each of these is a different amino acid building block that is put into the peptide while it's being produced, and this different combination then gives it the different properties that allow it to be an effective antibiotic. Now of course, peptides can be comprised of a very large number of beads. The example is shown here. You can see there's lots of different potential. We could build peptides, we could extend this peptide, make it longer, we could change its structure. And of course doing this gives us a different peptide which gives us different properties. Now understanding how this is made is very important if we want to then re-engineer the natural biosynthetic process to make new peptides. And so for simplicity's sake, what I'll do is show you basically how non-ribosomal synthesis works, which is very different to the ribosome. So the ribosome produces peptides such as this, but also a lot longer peptides and proteins. And this actually works in the way of a computer, where each of these would then be encoded by your DNA, which then gets decoded by the ribosome and installed into the peptide. But non-ribosomal synthesis works in a very different way. You can best think of it in this manner. So what we have here now is I have Lego building blocks, and you'll see that each of the colors roughly represents the beads in the peptide. Now what this actually is this is a symbolic representation of a peptide assembly machinery. And how this works is more akin to a factory assembly line, where each of these different blocks, or modules as they're known, is responsible for choosing and incorporating one of these specific beads into the final product. And of course this is a rather simplistic representation of a very large and complex assembly line, but this is actually the process that holds true for all non-ribosomal synthesis. And what that means is it's very easy. You could understand if we were to say, for example, delete this, we would actually then change the peptide into this. And so of course this means it's a very exciting system to play with if you want to re-engineer and produce new peptides. But in order to do that, we need to understand a bit more about how this machinery actually works. And what we have here now is a representation of what's known as a module. And so each of these small blocks actually is comprised of a different number of smaller units which have specific roles in terms of producing a peptide. And so what they do is, you can see here we have an orange, a yellow and a green block. The orange block underneath is responsible for joining these peptides and forming the chain. The green block actually acts like a hand, essentially passing amino acids from one unit to the next, whilst the yellow block is responsible for choosing the one that it wants. So you can imagine then, if we want to build this assembly line, we have to of course incorporate 7 of these blocks. Continue. This actually becomes quite a long assembly line, and that's actually true. In nature these are quite large and complex machineries. Now that we have everything here, what we can see is that each of these yellow domains will now activate the amino acid that it wants to choose. Once these have been activated, the secret to non-ribosomal synthesis is that then this green block essentially attaches to and binds these intermediates, so they can't float away. Now once these are all nicely attached, the machinery is then primed to make a peptide. And to do that, what happens is the orange block actually interacts these 2 green blocks together. In doing so, it transfers the orange block onto the downstream one. And of course now you can see we've built a dipeptide. And this is transferred down the line each time, extending it with one peptide bond, until at the end we have our final peptide, which is then removed and produced as so. And so you can imagine that understanding how this complex machinery works will allow us, for example, to add in additional domains. You'll notice I didn't talk about these blue ones. We could take them out, we could put them in, we can remove blocks, we can change the order, and in doing so, that will have a direct effect on the peptide that we produce. And so if we understand how these machineries work, we can take, for an example, of vancomycin and try to then re-engineer this to produce new compounds that will then be able to kill antibiotic-resistant bacteria. So hopefully from that demonstration you can now get some understanding of how these peptides are actually produced in nature. But of course what we're faced with is the reality that this is much more simple than a protein, and this is much more simple than a peptide. And so what we really need to do now is to understand the complex nature of how these machineries work if we're really going to be able to redesign these like assembly lines to make new compounds to fight against superbugs. Thank you very much for watching. I hope it was useful.